Our next topic in this unit is chemical reactions and how we write them and how we balance chemical equations. So to do these things, we need to first set some definitions about chemical reactions so we all know what we're talking about. The first thing I want to clarify for you is what a salt is. A salt is any ionic compound with a metal and a nonmetal, or a metal and a polyatomic ion. So table salt, NaCl, sodium chloride, is a salt, and when you put it in water, it breaks up and dissolves and becomes ions, and that's what this reaction here is showing you of NaCl breaking into a sodium ion and a chlorine ion. However, there are other types of salt in addition to simple table salt. You could also have magnesium fluoride, which in water would break into magnesium ions and fluoride ions. A common salt that we use during the winter in Colorado is calcium chloride, which is CaCl2, and we use it to salt our roads so that the snow and ice will melt faster. And when it dissolves in water, it forms Ca ions and Cl ions. So all three of these are examples of salts, and there are many other examples, obviously, that are not shown here. So if I'm talking about salt, or I say, well, it forms a salt, I'm not talking about table salt, sodium chloride necessarily. I'm talking about anything that has a metal and a nonmetal, or a metal and a polyatomic ion. In this class, we will classify reactions in several different ways, and we really only care about 5 types of reactions, even though there are many other types of reactions that we could cover. The 5 that we're interested in are composition reactions, decomposition reactions, single replacement reactions, double replacement reactions, and combustion reactions. And the remainder of these notes will be describing and giving examples of these 5 types of reactions. Composition reactions generally take the form A plus B equals AB. So you have an element or a simple compound and another element or simple compound combining to form one compound. So most of the examples we deal with will be one element plus a second element making a compound. And you could shorten this to E1 plus E2 equals C. There's lots of different ways to generically notate this. A specific example would be using hydrogen, H2, plus oxygen, O2, to make water, H2O. And so you've taken two things in their elemental form and turned them into a compound. Decomposition reactions are, as you might suspect, the opposite of composition reactions. So in a decomposition reaction, a compound breaks into 2 or more products. So generally, we could write that as AB goes to A plus B, or compound C goes to element 1 plus element 2. Some of these decomposition reactions are fairly complex. In the example here, we have ammonium nitrate decomposing to form nitrogen gas, water, and oxygen gas. And this is actually an explosive reaction, and many other types of explosions are also rapid decompositions. The reactions that we will be responsible for predicting in our class are relatively simple, where you have a compound and it breaks down to its elements. So an example of something I might ask you to predict would be the decomposition of water. And you would say, well, it's made out of hydrogen and oxygen, so it will decompose to form hydrogen gas and oxygen gas. Single replacement reactions are the next type of reaction, and within single replacement reactions we can consider a couple different types. We can consider metal replacement reactions and also halogen replacement reactions. First, we're going to consider metal replacement. In a metal replacement, you have an element A plus a compound BX, and A actually steals X away from B, and we make a new compound, AX, and then we have B left over. And so you can see that there's kind of just been a little bit of a flip-flop where the X has moved from the B to the A. A lot of the examples will be one element reacting with one compound to form a new compound and a new element. If an element is more reactive than the cation B that's in the compound, then A will replace B. However, if A is less reactive than B, nothing will happen. So for example, zinc is more reactive than copper, and so zinc can replace copper and bond with the sulfate, and then the copper goes back to its elemental form. So we've had an element reacting with a compound to form a new compound and a new element. It would be useful then, considering these reactions, to be able to predict how an element will react and to know if one element is more reactive than another element. To figure this out, we actually have something called the activity series, and a metal in the activity series can replace anything that is lower than itself on the list. So the most reactive things are lithium and potassium, and they can replace anything below them, such as chromium or iron or lead. And I will give you a copy of this list for you to use when you're solving problems in class. If you are doing a single replacement with something with a hydrogen, like an acid or water, then the top 4 elements on the list can replace the hydrogen and in water and acid. The next 5 elements can only replace hydrogen from acids, and the things below hydrogen on the list will obviously never replace hydrogen because they're less reactive than hydrogen is. The next type of single replacement reaction is a halogen replacement. So if you have a halogen, such as chlorine or fluorine, right here, and it's reacting with a compound, AX, then the halogen replaces X and bonds with A, and then whatever X was is now its own product. So for example, if we had chlorine gas reacting with sodium iodide, the chlorine would replace the iodide, and we would get sodium chloride and iodine as a liquid or a gas, depending on the temperature. The halogens activity series is actually just the 7th column of the periodic table. So fluorine is the most reactive, and the things below fluorine get increasingly less reactive. And I think it's worthwhile to mention that this makes sense based on what we know about chemistry. So if we think back to our periodic trends way back last semester, fluorine is at the top of the periodic table, which means it's very small. And we also know that fluorine is very electronegative. Because fluorine is very electronegative and really likes to gain electrons, the fluorine is able to attract the electrons from sodium more than iodine is, and that's why fluorine will react more strongly with iodine or with sodium than iodine will. And in this example, chlorine, which is also above iodine, would react more strongly than iodine and replace the iodine with itself. So the electronegativity is really the key to the reactivity, because fluorine is more electronegative and can more strongly attract electrons. It will actually be more effective as a reactant. The next type of reaction is a double replacement reaction. So here you have 2 cations, so 2 positively charged ions in 2 different compounds switching places. This is often referred to as a partner swap reaction because the anions switch their cation partners. Usually this happens in an aqueous solution. The general form of this would be a compound AX and a second compound BY reacting to form BX and AY. And so this little flip-flop of the cations is why it's a double replacement. Both of the ions are replaced. An example would look like compound 1 in aqueous solution reacting with compound 2 in aqueous solution and forming compounds 3 and 4. Now, when something is in aqueous solution, that means it's dissolved and dissociated, like the salts we talked about at the beginning of this lecture. So all of the ions are floating around in solution. So the ionic reaction of a double replacement will only occur if one of the new compounds is not an aqueous solution. So one of the new compounds would need to be a precipitate, a solid, a gas, or some other covalent compound like water. If, when you switch the partners of compound 1 and compound 2, if everything just stays in solution, dissolved, then nothing has really changed about the system, and so no chemical reaction has taken place. Combustions are the last type of reaction we want to talk about, and many combustions or burning reactions are possible, but the ones we're going to focus on in this class are hydrocarbon combustions. And hydrocarbons are anything that's made out of carbon and hydrogen, and often oxygen is also included in there. And so these include wood, paper, gasoline, candle wax, things like this. Generally, a combustion reaction will take the form of CH plus oxygen gas, which is in the air, reacting to form carbon dioxide gas and water. So in a perfect combustion, the only products you have are carbon dioxide and water. Carbon dioxide and water will always be the products of a reaction. So if I tell you that something is a combustion reaction, you can always predict the products of that reaction because they will always be carbon dioxide and water. Another thing you can always predict with a combustion reaction is that the second reactant will be oxygen. There are rare occurrences that we don't care about where other things are involved, but for our purposes, in a combustion reaction, you have a hydrocarbon and it reacts with oxygen. An example of this is propane. So propane is burned in furnaces and water heaters in homes that don't have piped natural gas like we do in the city. And so this propane is combusted with oxygen to give us carbon dioxide, gas, and water, and obviously heat. The formula for propane is C3H8, so we have this gas molecule that's reacting with the oxygen to give us carbon dioxide and water. Overall, we need to be able to classify reactions as to what type they are. So if you're looking at something that's two elements reacting, it's probably a composition. If it's a compound breaking into pieces, it's a decomposition. If you have one element and one compound reacting, it's probably single replacement. If you have two compounds reacting, it's probably a double replacement, and you're looking for cations being flip-flopped and precipitates or gases forming. And finally, we have the combustion reaction, which would have a carbon-hydrogen compound plus some oxygen, leading to carbon dioxide and water. These are the 5 things that you need to be able to identify and predict outcomes for moving forward in this class. On Friday, we're going to talk about how we write and how we balance chemical equations.